The AI research community just got hit with something that quietly changes everything about how we train reasoning models, and almost nobody outside hardcore ML engineering circles is talking about it yet. Moonshot AI, the same team behind Kimi, just dropped Seer, a new reinforcement learning infrastructure system that fixes one of the most painful bottlenecks in training large language models. And the numbers are honestly wild. We're talking 74% to 97% throughput improvement and up to 93% reduction in long tail latency. That's not a typo. Let me explain you why this matters and why every AI lab running reasoning models should be paying attention right now. So here is the problem Seer solves. When you are training modern reasoning models like GPT or Cloud using reinforcement learning, the process happens in iterations. The model generates responses, those responses get evaluated, and then the model updates its weights based on feedback. Simple concept, right? But the actual execution is a nightmare. The part that kills performance is called the rollout phase. That's when the model generates multiple responses to the same prompt in parallel. And these phases can eat up to 63% to 87% of your entire training iteration time. The issue is workload imbalance. When you ask a model to generate responses, some finish in 500 tokens, others go 5000 tokens, and a few strugglers push past 10,000. Traditional systems assign entire groups of requests to specific GPUs and just wait. So you end up with some GPUs finishing early and sitting idle while one or two machines are still grinding through long responses. Your expensive H800 clusters is burning power and most of it is doing absolutely nothing. That's the bottleneck. Moonshot researchers look at this problem and realized something everyone else missed. Requests that share the same prompt tend to have correlated output lengths. If you are generating reasoning traces for a math problem, most answers cluster around similar length. Some are short, some are long, but they are not random, and nobody was using that pattern as signal. Seer exploits this by introducing what they call online context learning. The system learns during the rollout itself and adjusts scheduling dynamically instead of treating every request like an isolated event. Here is how it works. Seer breaks down the rollout into three core techniques. First is divided rollout. Instead of assigning entire request groups to one GPU and waiting for everyone to finish, Seer decomposes groups into individual requests and then splits each request into chunks. So instead of locking a GPU to a 10,000 token generation, it processes 8,000 tokens, requeues the request, and moves on. This keeps GPUs busy and eliminates idle time. The second piece is context-aware scheduling. Seer designates one request per group as a speculative request. It runs these first with high priority and tracks how long they take. If a speculative request finishes quickly, the system knows the group is probably short and schedules the rest aggressively. If it takes forever, Seer flags the group as a potential tail case and adjusts the schedule to handle it intelligently. This approximates what researchers call an oracle scheduler, which would magically know every request length in advance. And the crazy part is, Seer's online learning gets within 95% of oracle performance without any pre-knowledge. The third technique is Adaptive Grouped Speculative Decoding. This is where it gets technical. But stay with me. Speculative decoding is a method where the system drops tokens quickly using a smaller or faster model, then verifies them with the main model. Seer does this at the group level, using tokens from one request to predict tokens for another request in the same group. And because those requests share context, the acceptance rate is much higher than random speculation. The system adapts dynamically, adjusting how many tokens it speculates based on how well previous attempts worked. In later stages of a rollout, when the system has learned more about the group, speculative acceptance jumps from around 1.7 tokens per step to 3.5 tokens. Now let's talk results, because this is where Seer separates itself from theoretical improvements. Moonshot tested this on production-grade workloads using three different models: Moonlight, Quinto VL72B, and Kimi K2. These aren't toy benchmarks. These are real reasoning RL tasks running on 32 compute nodes with 8 H800 GPUs each. That's 256 GPUs total. The baseline they compared against was VRL, which is already considered state-of-the-art for synchronous reinforcement learning and uses VLLM under the hood for inference. On Moonshot, Seer improved end-to-end rollout throughput by 74%. On Quinto VL, it hit 90%. On Kimi K2, 97%. And tail latency, the absolute worst case response time that defines your slowest iteration, dropped by 75% on Moonlight, 86% on Quinto VL, and 93% on Kimi K2. To put that in perspective, the baseline system was spending up to half of its time wasting on the last 10% of request. Seer removes almost all of that tail. The research team ran ablation studies to break down which components contributed the most. When they disabled Adaptive Grouped Speculative Decoding, throughput dropped 27%. When they removed context-aware scheduling, it dropped 11%. And when they tested divided rollout along with any context learning, it still provided major gains just from better load balancing. This tells you that every piece of the system is doing real work. It's not just one clever trick. It's a cohesive architecture where the techniques reinforce each other. What makes this especially important is that Seer doesn't change the underlying reinforcement learning algorithm at all. It uses GRPO, which is a standard synchronous RL approach. That means it preserves from policy guarantees and reproducibility. A lot of recent research has tried to speed up RL by going asynchronous, which overlaps the rollout and training phases. That can improve iteration time, but it introduces off-policy drift, which means your model is learning from slightly stale data. That's fine for some applications, but for research or production systems where algorithmic fidelity matters, it's a problem. Seer gives you the speed of asynchronous systems without sacrificing correctness. The system also integrates with Mooncake, which is Moonshot's KB cache management framework that won Best Paper at FAST 2025. Mooncake enables disaggregated serving, where the key value cache used during inference is stored in a global pool instead of being tied to individual GPUs. This is critical for divided rollout because requests can move between machines without losing their cached context. The combination of Seer's scheduling and Mooncake's memory architecture is what makes the whole thing work at scale. Now, why does this matter beyond just Moonshot's internal infrastructure? Because reasoning models are everywhere now. OpenAI's O1, DeepSeek R1, Google's Gemini thinking mode, Anthropic's extended thinking, all of these use long chain of thought reasoning, and all of them rely on reinforcement learning during training. The longer your reasoning traces, the worse the rollout bottleneck gets. Seer directly targets that. If you are an AI lab training reasoning models, this paper gives you a practical template for how to structure your RL stack. Moonshot has been on an absolute tear lately. Kimi K2 with its trillion parameter MOE architecture, Mooncake winning Best Paper, and now Seer. They're building the full stack, from model architecture to training systems to serving infrastructure. The paper is available on arXiv, and the research team includes folks from both Moonshot AI and Tsinghua University. If you are working in ML infrastructure or you are curious about how modern RL systems actually work under the hood, this is required reading. The techniques are modular enough that you could implement pieces of this in your own stack without adapting the whole thing. One thing I'm curious about is how this scales beyond reasoning models. Seer is designed specifically for long context chain of thought workloads. But could the same principles apply to other domains where you have grouped requests with correlated characteristics, multimodal generation, code synthesis, agentic workflows? The core idea of online context learning feels general enough that it might transfer. That's where we will wrap it up. Seer is one of those systems contributions that doesn't get as much hype as a new model release, but it's the kind of infrastructure work that makes the next generation of models possible. Drop your thoughts below. If you are working on RL systems or you have hit similar bottlenecks in production, I would love to hear how you are tackling it. Make sure you subscribe, hit the like button, and I will see you on the next one.